Hello, I'm Eric Clausen, and I'm the author of the topographic map mystery, Geology's Unrecognized Paradigm Problem. And in this lecture, I'm going to talk about a problem that geologists, at least most geologists, don't recognize that the geology research community has. And that problem is that geologists, for the last 60 years, have been ignoring the topographic map, drainage system, and erosional landform evidence. The topographic maps represent probably the best way to observe that evidence. And an example of the evidence that's being ignored is shown in the map that I've illustrated here. And this dashed red line that you're seeing here is the Continental Divide, and this is located in the high Colorado Rocky Mountains. It's near Rocky Mountain National Park. And we're looking at a very deep valley that's cut across the Continental Divide here, known as La Poudre Pass. Now, if we look at the Continental Divide, it's a very well-known feature. And like many other drainage divides, it's a major drainage divide. Geologists know it's there. They can describe it in great detail. It's been mapped in great detail, but geologists cannot provide a real good explanation of how, why, and when it was formed. And the same thing is true of La Poudre Pass here, which links, it's a valley linking the Atlantic Ocean drainage basin with a Pacific Ocean basin. It's a very deep valley, hundreds of feet deep. And at one time, water flowed across this valley. But how it got across this valley, what the details of that are not well understood by the geology research community. So this is the problem that I want, and this is a very common problem. And this is the problem that I want to discuss with you today, and I'm going to introduce it to you. Now, the book on which this lecture is based and any future lectures that I give on the subject is titled The Topographic Map Mystery, Geology's Unrecognized Paradigm Problem. And in the book, I illustrate dozens of examples of similar topographic map drainage system and erosional landform evidence, which is scattered all across the United States, that the accepted geology paradigm does not satisfactorily explain. Now, in the lecture, I'm going to emphasize Philadelphia and Pennsylvania area topographic map drainage system and erosional landform evidence, much more so than the book does. But I could have picked any other region, just about any other region of the United States, and showed examples from it. Now, I want to start out by looking at a topographic map and just explaining a few things about reading topographic maps. This map here is an area on the north edge of the city of Philadelphia, and we're seeing Wissahickon Creek here flowing in a south direction into the city of Philadelphia. And this particular area is a Philadelphia park, and there's a very deep gorge that Wissahickon Creek flows through. It's a very scenic area that lots of Philadelphia residents like to hike in today. Now, in terms of the map, the features that you need to be aware of is that you'll see lots of lines on the topographic maps. These are contour lines, and they're drawn with the idea of connecting all the points of showing on the map all the points of a certain elevation. Now, on this particular line that we're seeing here, all the points on that line are 300 feet above sea level. And so this is the 300-foot contour line. If we come up the slope here, we find that there's the 350-foot contour line, and this is a closed contour line. It makes a circle, and this indicates that we're at the top of a hill here, so that we can determine whether we're going up or down by looking for features like this. Now, if we look at the contour lines here, we can see that we're We've got contour lines going down 350 feet, 300 feet, 250 feet, and 200 feet here. So we've got a slope going down and the contour lines are spread out. If we come over here, the contour lines are much closer together. And so we're seeing a much steeper slope. If we come up here, the contour lines are um, almost missing. So we're looking at a relatively flat area. So in terms of the maps that I'm going to be showing on during the lecture today, that's basically all you need to know. And a lot of what I'm going to be talking about is drainage systems. And what's important is just being able to recognize where the rivers are flowing, as in this case, Wissahickon Creek is flowing here. Now, there's some odd things about Wissahickon Creek that are anomalous evidence. Just on this map here, Wissahickon Creek is entering this steep gorge here that's probably 300 to 400 feet deep in places, and it's cut into very erosion resistant rock. It's entering this gorge at this point, even though it's just crossed a wide flat area, which extends in a west direction to the Schuylkill River Valley, and Wissahickon Creek could have flowed in a west direction and avoided having to cut this gorge here completely. So that's anomalous evidence. Geologists rarely try to address why Wissahickon Creek is flowing where it is now, rather than flowing in another direction, which would have avoided cutting the gorge. Another feature here that is anomalous evidence is that there's this minor tributary here that flows in a northeast direction to join the south-oriented Wissahickon Creek. Usually, you'd expect the tributaries to join the creek to be flowing in the same direction as the creek is flowing. But in this case, it's flowing in the opposite direction, and that needs an explanation. And geologists ignore that evidence because they don't have a good explanation for it, at least within the context of the accepted paradigm. Let's now turn to what science is very briefly. Science is a systematic endeavor that builds on and organizes knowledge in the form of testable explanations and predictions about the universe or about nature. And testable in geology may have a different meaning than it does in some other scientific disciplines where you can prove a hypothesis is correct or false. In geology, as most hypotheses cannot be proved whether they're correct or false. All we can do is accumulate evidence that supports the hypothesis, or we can find evidence that does not support the hypothesis, but we can never prove with certainty whether something is true or something is not. And that's because the Earth is huge. We can't reach all areas of the Earth, especially the Earth's interior. And also, the Earth has a very long history, and there's no way we can go back and test to see whether an event that we think happened actually happened. Now, scientific paradigms are, which I'm going to be talking about in quite a bit of detail as we go along, are sets of rules and assumptions. They establish a framework or perspective that defines how a scientific discipline looks at nature. Now, in geology, there's a framework of ideas, which also establishes a terminology. And this framework enables geologists to communicate with each other, and it also enables them to build upon each other's research. And without a paradigm, the geology community would not progress. So a paradigm is very important to a scientific discipline, and they're going to work hard to protect their paradigm. but paradigms are not always correct. There's no guarantee that a paradigm is correct. And to give you an example from the astronomy field, as you may be aware, that astronomers for much of history thought that used a Earth-centered model, where, and this was proposed by Ptolemy, um, all more approximately 2,000 years ago. And this model explained all of the solar system object movements in the context that they were moving around the Earth in circular orbits. Now, as astronomers got better and better observations throughout time, it became apparent that this model didn't explain all of the observations. And so astronomers added complications to the model, and these complications involved epicycles, such as you see here with Jupiter, where Jupiter was making these loops here that you see. And the model was becoming very complex as you got to about 1200 or 1300, and into the 14th century. And these complexities caused especially Islamic astronomers to question whether this model was correct. They didn't come up with a better model, but they were raising a lot of questions about this model, saying it's too complex. There's got to be a better way to explain it. And Copernicus did come up with a better way to explain it. And he put the sun at the center, and he had the Earth and the other planets moving around the sun. Now, initially, the Copernicus model it didn't explain the astronomical observations any better than the Ptolemaic model. And that's because the Copernicus model still wasn't perfect. Kepler perfected it some by coming up with elliptical orbits, and then Newton developed some additional improvements. And with those improvements, there was no question that the Copernican model was the superior model, and so the Ptolemaic model collapsed and ended up being abandoned. And this is the model that we use today, and it's a very successful model, and without it, our space program wouldn't be in existence. Now, what is a paradigm and how is it constructed? Well, I view a paradigm something like this building. And you can't see the foundation of the building, but there's somewhere down here, there's a foundation, which was started in the case of the geology paradigm, probably in the 1700s, with James Hutton and other early geologists. And they developed some ideas upon which they could agree that they could build share ideas, and some terminology that they agreed to share. And based on those fundamental starting ideas, additional geologists built new ideas, and they kept each interpretation is like a pillar here. And then these pillars enabled additional pillars to be built on top of them. So it's a great paradigm is a great big building of ideas and interpretations that are resting on a foundation somewhere down here. And as the science progresses, the scientists are busy working up here on the upper levels, and they rarely go back down to check to see whether the pillars that their work is being based on are solid or not. And they just assume that the previous work is solid. And so this is what the paradigm, at least in my view, looks like. And much of the scientific work is really fleshing out the paradigm, which is basically filling out the space and the empty spaces that you see here with details of observations that support the key ideas in that level. Now, moving on, how does the paradigm get defined? There is no governing body that defines the geology paradigm or any other scientific paradigm, although in the case of geology, there are government agencies, publishing houses, professional associations, and even university geology departments that may have procedures for defining the geology paradigm for their purposes. Within the larger geologic research community, the paradigm is defined and determined by what gets published in geology textbooks, geology journals, and government agency publications. And there's usually some kind of a peer review process that, among other things, is aimed at protecting the accepted geology paradigm from any radical shifts or ideas, but it's a very undefined process. Also, funding agencies often define what research gets funded because geologists, like all scientists, follow the money and they will neglect research subjects for which there's little or no funding. So, research agencies, especially in today when much of the scientific research is funded by the government, government funding is defining what the paradigm is. There is a problem that paradigms have. While paradigms are essential for every scientific discipline, though there is a problem that all disciplines encounter from time to time, and that is when their scientists are doing normal science, and that is fleshing out their paradigm. From time to time, they run into evidence that cannot be explained by the paradigm. Or it cannot be satisfactorily explained. And this is what Thomas Kuhn calls anomalous evidence. And this is something that occurs in all scientific disciplines, so it's not unique to geology. And here's a map that was produced by the United States Geological Survey in the 1890s, and it's of the Shamokin, Pennsylvania area. This is Shamokin, Pennsylvania here, and this is the Susquehanna River flowing in a west direction here, and it will turn in the south direction here. And on this map, there's a fair amount of anomalous evidence, but the evidence that I'm going to comment on is Shamokin Creek, which starts here in the Shamokin area, and it flows north through a deep water gap that's been cut across Big Mountain, which is this ridge that you see here. And then Shamokin Creek makes a jog here to the west, and then it turns north again, and it's cut another deep water gap across another high ridge or mountain known as Little Mountain, and then it continues in a north direction. It's cut another water gap across this ridge here, and then it continues up here and then turns in a west direction to join the Susquehanna River that flows in a south direction over to the west here. Now, Shamokin Creek is a relatively small drainage system, and what geologists cannot explain is how Shamokin Creek was able to cut these three water gaps that I pointed out. The water gaps are known, they've been mapped in great detail, not only this map, but more recent maps show them the water gaps in much more greater detail. The rocks in the area have been mapped by geologists, so geologists can tell you a lot about the geology of the area, but they cannot tell you how Shamokin Creek was able to erode these water gaps. So this is anomalous evidence, and geologists have tried to explain this evidence, but and evidence like it, which is scattered, as I said, all across the United States. And finally, they gave up on trying to explain it And as a result, for the past 60 years, there's been virtually no research related to the origin of the water gaps, such as these water gaps. Now, according to Thomas Kuhn, anomalous evidence is dealt with in one of three ways. The evidence may eventually be explained by the paradigm, and if so, the paradigm will survive without any major interruption. The evidence may be noted and set aside, and that's basically what's happened here. The evidence has been noted, it's been mapped in great detail, and it's been set aside in the hope that at some future time somebody will explain it. And then, um, uh, but nobody has been trying to explain it, so it's not being explained. The evidence could lead to a new paradigm, and in that case, there's almost certainly going to be a battle over which paradigm should be used. So those are the three options that are available for explaining that evidence. Geology, as you probably know, is the scientific study of the Earth, and it's been expanded in recent years to include the study of other rocky planets and rocky type moons. There are many subdisciplines of geology, many of which have no bearing in the discussion that I'm going to have here. The subdisciplines that are important in this discussion are historical geology, geomorphology, and glacial geology. Now, historical geology deals with determining the Earth's history, and the part of Earth history that we're most important that probably is most important to drainage system and erosional landform evidence is the Earth history since the dinosaurs became extinct. And geomorphology deals with the Earth's surface features, and the type of Earth's surface features that are most important to the discussion here will be drainage systems and erosional landform evidence. And glacier geology relates to glaciers and ice sheets, and the geology of those that is related to those glaciers and ice sheets. And most importance here are probably the ice sheets that covered North America during the what the accepted paradigm considers to be the Quaternary epoch. Now, geology, as I've said, is a science and is subject to the rules of science, although because of the Earth's size and its very long history, the testing of many geology hypotheses is very difficult. There are some rules that need to be followed when geological research is being done. And just briefly, some of these rules are geologic evidence that's being interpreted must exist, and it must be observable by anyone who takes the time and makes the effort to look. Then all pertinent evidence must be addressed to the maximum extent possible. Now, this rule is a very difficult rule to follow because it's hard to know what is pertinent evidence, and also because the volume of geological evidence that's available, it's hard to know what to include all of the evidence, and hopefully you try to get a representative sample of the evidence. Another rule is that common sense logic must be used when making interpretations, and that those interpretations must include logical steps without any gaps in the logical sequence. Then the fourth rule is that all evidence must be interpreted in a consistent manner, and that means you can't interpret one feature one way and then find and interpret another similar feature in a different way, unless there's a very good reason to do so. The fifth rule that I think is worth noting is that when evidence can be explained by two or more explanations, the simplest explanation should be preferred unless there's a very good reason for not using it. And then the sixth rule is one that was developed for geologists in the 1890s, and this is called the method of multiple working hypotheses. And this is when a geologist is interpreting a set of evidence, the geologist should consider all the possible interpretations, not just the first one that comes to mind. And so the geologist should come up with multiple hypotheses to explain the evidence and then test all of those hypotheses so that the geologist doesn't come up with a favored hypothesis right off the bat. So those are some rules that I try to follow. As I said, some of them are very difficult to follow because of the size of the Earth, the volume of evidence that's available. But there are things that I think anyone doing research needs to be aware of and um, be prepared to defend when they are discussing their research. Now, I want to turn now to some of the problematic accepted geology paradigm interpretations. And many of the problems that are that arise from when trying to interpret topographic map, drainage system, and erosional landform evidence arise because of accepted paradigm interpretations related to North America's glacial history. Now, the location of the ice sheets is not problematic. The topographic map evidence and the accepted paradigm interpretation of where the ice sheets were are pretty similar. And so there's no real problem about where the ice sheets were. But the accepted interpretations are related to the number of ice sheets is a problem. The accepted paradigm, as I will illustrate in the next few slides, assumes that there were multiple glacial and interglacial episodes during the Quaternary when we had ice sheets, then interglacials, ice sheets, interglacials, ice sheets. The problem and the number of interglacial glacial cycles varies depending on what reference you're reading, but that all of the accepted paradigm interpretations are that there were multiple glacial, interglacial cycles. And that's a problem when interpreting topographic maps. Another problem is how deeply the ice sheets eroded. And as I'm going to point out in some of the following slides, that when you the accepted paradigm sees valleys which are in the glaciated areas here that are abandoned valleys now filled with sediments that glaciers obviously deposited, that they interpret those abandoned valleys to have been eroded by pre-glacial drainage systems. And if those abandoned valleys are still visible today, that means that the ice sheets did not erode the continent very deeply in this area. Now, this creates a major problem when interpreting topographic maps. And also, there's another problem, and that is the accepted paradigm generally is very conservative in terms of the amount of meltwater that flowed from the ice sheets. There are evidence of large floods in a number of places along the ice sheet margin where glacial lakes failed and produced short-lived floods. But on the whole, the amount of meltwater that the ice sheets produce is that the accepted paradigm sees. It limits where the meltwater went. And the topographic map evidence suggests that the meltwater went in many places that the accepted paradigm doesn't see meltwater going. Now let's look at some of these problematic interpretations in the accepted paradigm. And this is the Missouri River Valley, or the northern Missouri River drainage basin in Montana, North Dakota, South Dakota, and Wyoming. And you'll notice the Missouri River is an asymmetric drainage basin here with long north and northeast-oriented tributaries, and even a north-oriented headwaters. And the reason for this is that as the Missouri River is in the accepted paradigm interpreted to be an ice marginal river, that it formed along the margin of an ice sheet that blocked north-oriented pre-glacial drainage systems that were flowing down a north or northeast-oriented slope. So the slope in this whole area, as I'm going to show you in the next slide, is a northeast-oriented slope. And there's some logic to this because there's evidence for abandoned valleys. I'll show you an abandoned valley here in northwest North Dakota in the next slide. And that valley does have glacial sediments in it. So there's a case here for this. But as I said, this creates problems when interpreting the topographic map evidence. Well, let's look at that northeast-oriented slope that that the drainage routes flow down. This is the state of North Dakota, and this is a relief map, and the colors are showing elevations, with the highest elevation here in white, and then the lowest elevations in green. And these elevations are shown in meters. So this is 1,000 meters, and so this is over 3,000 feet. And this area here doesn't get much higher than that in North Dakota. And this is the highest point in the state. And the lowest point in the state is right here in the northeast corner of the state. So there is a very visible northeast-oriented slope here. And I want to point out here that this feature here, this is known as the Missouri Escarpment, and it's a step from low plains here to higher plains on the other side. It's a step of about 100 to 200 meters, or 300 to 600 feet. It's a gradual step, and there are places where you can drive across it and hardly know that you're crossing it. Other places it's quite noticeable. But even the places where it's not so noticeable, the railroads, when they came across this North Dakota, they sure noticed it because they were gaining elevation as they went up the escarpment. And this is a very major feature. It continues down into South Dakota, almost to the southern South Dakota, and it continues in a northwest direction into Saskatchewan and all way into Alberta, and it's almost 1,000 miles long. So it's a major feature which has never been adequately explained by the accepted paradigm. And if we look over here, we're seeing the Turtle Mountains. This is an isolated upland area. It's surrounded by escarpment very similar to this escarpment here, and the elevation here is similar to the elevations here. In fact, the type of glacial deposits are very similar also. And this hasn't been really adequately explained either. Now, if we look at the Missouri River, here's the Missouri River course across North Dakota that you're seeing. So it's not going downhill. And it's definitely flowing. It's something as unusual as happened here to block the north-oriented drainage. And here's that abandoned north-oriented valley that I told you about that extends north from the Missouri River Valley. And it can be traced off and on up into Canada and across Canada. Whether it's the same valley as you go further can be debated, but there are definitely valleys like this that can be seen. And there are glacial sediments in here, so there's no question that ice came down here and partially filled this valley. So let's look at what it looks like underneath this. And here we're looking at a greatly exaggerated vertical cross-section of the bedrock units that are underneath North Dakota. And To give you, this is 10,000 feet below sea level. This is 1,000. This is sea level. This is 2,000 feet above sea level. I think this is exaggerated a little bit because North Dakota doesn't get quite that high, but that we're looking at basically the highest point in North Dakota here at the southwest corner of the state and the lowest point in the state at the northeast corner of the state. And the rocks that we're seeing here, these brown rocks, these are Paleocene rocks. And these formed after the dinosaurs became extinct. The Paleocene, the Cretaceous tertiary boundary is this boundary right here. This is when the dinosaurs became extinct. And we've got a very, in the southwestern part of the state, we've got a thickness of Paleocene rocks that's almost more than 2,000 feet thick in places. And as we come further east, it gets thinner. And this is an erosional edge. In other words, the beds have been eroded away, implying that these Paleocene rocks once extended much further to the east. And underneath these Paleocene rocks, we have Cretaceous rocks. And these Cretaceous rocks, there's a great thickness. Here we've got probably 2,000 feet or more of Cretaceous rocks. And these are, as we come further east in North Dakota, these also thin out. And again, it's an erosional edge, implying that the Cretaceous rocks once extended much further to the east here. Now, today, because they're glacial deposits on top of this erosional surface, the accepted paradigm assumes that the northeast-oriented slope here existed before the glaciation. And so this is assumed to have developed during tertiary time, probably sometime after the Paleocene. And if we look at the rocks that are older than the Cretaceous, we find that there are erosion surfaces shown with these wavy lines that are older erosion surfaces, but they don't seem to be, the beds don't seem to be particularly thick when we get over into the eastern part of the state. So they're not really significant. And also we're dealing with periods of geologic time periods long before the glaciation. So they're not really significant to what we're talking about here. Now, looking at before we leave North Dakota, I want to talk about a problem that bothered me. I used to teach at a university located about here, and I always was bothered by the fact that the Missouri River was not at the ice margin, even though it's supposedly an ice marginal river. This is a map of glacial deposits in North Dakota. The different colors show different types of glacial deposits, but the southern and westernmost margin of the mapped glacial deposits is roughly along this line. You can debate whether this line is correct, but there's a pretty general agreement that it's somewhere in this area. And why, if the glacial deposits got this far here, why didn't the Missouri River form along the edge of the glacier that carried these glacial deposits out here? There's no question that there are glacial deposits here. On this side of the Missouri River, the glacial sediments are largely coarse-grained, and many of them are boulders or cobble sized or large gravel. But there are good sized boulders, some of them the size of a car, that are scattered across the landscape here. So it's pretty well accepted that glaciers got to the south and west of the Missouri River, but there's no valley here indicating that there was an abandoned Missouri ice marginal river. And there's also, and there's no reason why the Missouri River should be where it is. So there are problems with the accepted interpretation. And if we come to the northeastern United States, I'll just briefly mention here, this is Pittsburgh here, where the Allegheny River comes down south here and joins the north-oriented Monongahela River, and they form the Ohio River, which now comes up to here and then turns in a west direction along the margin of where the ice sheet outer margin has been mapped here. This is a 1903 map, but the ice sheet margin is pretty much hasn't changed much since this area was mapped. There's been quite a bit of map of investigation of the ice glacial deposits, but the margins have stayed pretty much the same. But the accepted paradigm interpretation in the 1890s, and it's still today, is that the Monongahela River used to flow in a north direction here up into the Lake Erie Basin, and then it flowed somewhere, maybe in an ancestral St. Lawrence drainage system off in this direction here. And that these other colored drainage basins are showing what were north-oriented drainage basins previous to the glaciation. And if we look over here at the Susquehanna River drainage basin, it starts in areas that were recognized to have been glaciated, and it flows down out of the glaciated area into Chesapeake Bay. But the accepted paradigm interpretation is that the Susquehanna River existed before glaciation. And the same thing is true of the Delaware River. So there's no question that in the accepted paradigm that glacial meltwater flowed down these rivers and maybe modified the valleys somewhat, but the rivers are thought to have existed prior to glaciation. Now, looking at a map showing where some of the river valleys across Canada are, pre-glacial valleys are across Canada, this is showing what is the generally accepted interpretation of the pre-glacial drainage system. And as I said, there is evidence for valleys in many of these locations, and these valleys are filled in where they're found with glacial sediments. Whether it was exactly like this can be debated, but there's no question that there are abandoned valleys here that are filled with sediments. Now, this map also shows how geologists are building on that accepted paradigm interpretation, because the geologists who produced this map wanted to propose that the Colorado River, which is flowing here, he's proposing that it made a turn in the Grand Canyon area and flowed north up through Montana, and then joined this pre-glacial drainage system to go north to the Hudson Bay and Hudson Strait area. And he's published several papers describing this. And so he's trying to extend the paradigm, expand the paradigm and build another pillar on it here. This has not been accepted by all geologists at this time, but he's trying to build a case for it. And he may succeed, I don't know. Now, this interpretation that the northeast slope existed prior to glacial time is very important in the way geologists define time in the Cenozoic era. And the Cenozoic era is the time period since the dinosaurs became extinct. and geologists subdivide that into a tertiary period, which covers all but the last roughly 2.6 million years of the Cenozoic. The Cenozoic started about 65, 66 million years ago. And then the Quaternary period, which is the last 2.6 million years, which consists of the Pleistocene or the Ice Age, and the Holocene, which is the most recent epoch, which is since the last ice sheet melted. Now, the Tertiary has been subdivided into a number of epochs, and I showed you the great thickness of Paleocene sediments that are in North Dakota. These other sediments, have been mapped in North Dakota. I debate whether they're there, but that they've been mapped there and in the accepted paradigm mapping, and that they're very thin in North Dakota, but we're talking probably about 50 million years of Earth history in here, 40 to 50 million years of Earth history. Anyways, this is the way it's been subdivided. These are subdivided based on mammalian fossils, and the vertebrate paleontologists are very insistent that that's a very good subdivision. Looking at the glacial deposits that were used to define the glacial interglacial cycles, the evidence in North America started out in the 1890s when geologists were first mapping North American glacial deposits. And they noted that a lot of the glacial deposits were very freshly looking, and so they considered that these had been deposited by the most recent glaciation, which they called the Wisconsin glaciation. And then they found on the edge of these deposits, especially in Illinois, somewhat in Indiana and Ohio, and also in Pennsylvania, glacial deposits that looked to be more weathered and eroded, and they called these the Illinoisan glacial deposits associated with an Illinoisan ice sheet, which was earlier than the Wisconsin ice sheet, and they assumed that there was an interglacial between these two ice sheets when these deposits were eroded and weathered. Now, they further mapped areas in Missouri, Iowa, and Nebraska and Kansas, and they found even more weathered and glacial sediments. And these they subdivided into two different glacial periods, the Nebraskan and the Kansan. And this evidence was used to establish the idea that there were glacial cycles. We'll talk about that in the next slide, but similar evidence is not been found. Similar evidence was found in Europe, but it's not identical. And in the U.S., what they came up with was initially this glacial interglacial cycles that you see here, starting with the Nebraskan being the oldest glacial period, then interglacial, then the Kansan ice sheet, then an interglacial, then the Illinoisan ice sheet, and then interglacial, and the Wisconsin ice sheet, and now the time since the last ice sheet, the Holocene. Now, this was commonly shown in many textbooks for many, many years. It's now frequently considered obsolete. And so if you see it in a textbook, it's probably an older textbook. But that the concept of glacial interglacial cycles is still very strongly part of the accepted paradigm, except now Using oceanographic sediments, geologists think that there were many more glacial interglacial cycles, and also there's evidence on other continents and other locations in North America, which are defined somewhat differently. And while there's while there's a lot of disagreement about how many glacial interglacial cycles there were, there is a general agreement in the accepted paradigm that there were a number of these glacial interglacial cycles. And as I said, this creates problems interpreting the topographic maps. Well, with that introduction to some of the problems that arise when interpreting topographic maps, I want to move and conclude the lecture by following the Delaware River downstream and showing you a number of direction changes which are poorly explained by the accepted paradigm. And we start out in the Delaware River headwaters area where the west branch of the Delaware River starts out in the Catskill Mountains. It flows primarily in a southwest direction. It doesn't look too southwest here, it looks more west here. But if you look at a larger area, it's definitely a southwest-oriented river, and it's coming here to deposit New York, where it all of a sudden turns in a southeast direction, comes down here to Hancock, New York, where it joins the east branch of the Delaware River, which also starts in the Catskill Mountains, and it's primarily a southwest-oriented river before it gets to this point. And then it turns in a southeast direction after it joins the west branch of the Delaware River. And now we have the Delaware River itself flowing in a south and southeast direction. And let's follow it downstream. Here we're picking it up, and it's following the Pennsylvania-New York border here. And we're coming down here, and we get to Port Jervis, New York, where the Delaware River enters a broad northeast, southwest oriented valley, which is controlled by geologic features. So, and there's a high ridge here that is composed of resistant rocks. And you could say that the Delaware River makes this bend because of this ridge. But we'll follow this ridge and the Delaware River in a southwest direction along the Pennsylvania-New Jersey border and see what happens as we get down to the Stroudsburg, Pennsylvania area. This is Stroudsburg, East Stroudsburg. And here the Delaware River is in the valley between this ridge, which is known here as Kittatinny Mountain, and Pocono Mountain Escarpment. And instead of continuing in the valley, which continues in a southwest direction here, the Delaware River all of a sudden turns in a southeast direction and cuts a deep water gap across Kittatinny Mountain and flows in a southeast direction here. And that this water gap is a very well-known feature. It's been studied in great detail. And geologists can tell you an awful lot about the geology of this region, but they can't give you a good explanation for how the Delaware River was able to cut that water gap. There are hypotheses out there, but they're not generally accepted by most geologists. And if we continue in a southeast direction from the Delaware Water Gap, which is right up here, this is Kittatinny Mountain here, we come in a southeast direction, and all of a sudden the Delaware River turns again in a southwest direction. It makes a jog here. And why the Delaware River makes this turn here isn't real clear. You could maybe argue that there's some geologic features here that account for it, but that's not as strong an argument as we could make up at the Port Jervis area. Let's follow the Delaware River down in a southwest direction to the eastern Pennsylvania area. This is eastern Pennsylvania, and this is Phillipsburg, New Jersey over here. And over here is um, Bethlehem, Pennsylvania. And this is the Lehigh River flowing in a northeast direction to join the south-oriented Delaware River as a barbed tributary. And as you remember, I said that barbed tributaries where stream flow joins another stream in the opposite direction that the main stream is flowing is an unusual feature, and it needs an explanation. And this has never been adequately explained. And also, if we look closely here, we can see that the Delaware River has cut more water gaps across ridges here and down here and further down here. So let's follow the Delaware River further south. Easton is here. We're following it south. It's cut numerous water gaps. These are not as spectacular as the Delaware water gap, but they are water gaps. And so the Delaware, and all of these need explanations, and they've never been explained. And as we continue southward, we're cutting more water gaps here. Some of them are across geologic structures like Kittatinny Mountain, although they're not as high as Kittatinny Mountain. And some of them are across igneous intrusions. And we get down here, this is Lambertville, New Jersey, and this is New Hope, Pennsylvania. And let's continue southward to Trenton, New Jersey. And here the Delaware River makes an abrupt turn to the southwest for no reason at all. And there's no geologic structure here that accounts for this bend. That the Delaware River logically should just continue in a southeast direction, or at least a south direction here, and not turn in a southwest direction to flow towards Philadelphia. But this bend is made, and some geologists have tried to explain this by suggesting that the Hudson River once flowed in a southwest direction across New Jersey, and there's some evidence that there was a lot of water that flowed in a southwest direction across New Jersey, and that this was originally the Hudson River route, and the Delaware River came in as a tributary to the southwest-oriented Hudson River, although not all geologists agree with that. And I'm going to show you in the next slide evidence that leads me to believe that that's not a correct explanation. Now here, this slide shows a much bigger area, and here you can see the Delaware River making its bend at Trenton. And here we're looking at some of the other drainage routes in the area, and one of the major tributaries in southeastern Pennsylvania is Neshaminy Creek, which starts out with two southeast west oriented branches, and then it turns in a southeast direction, somewhat parallel to the Delaware River here, and then it turns south to join the Delaware River. If we look at Wissahickon Creek over here, it starts out in a southwest direction, and then it comes down here and flows somewhat in a southwest-east direction as it enters Philadelphia. The map that I showed you at the beginning was right in this area here, and but just it's still in the gorge, but before it enters, before it reaches the Schuylkill River, the gorge makes a sharp bend to the southwest, just like the Delaware River does over here, and the Wissahickon Creek joins the Schuylkill River as a southwest-oriented stream. And the Schuylkill River is flowing here in a southeast-oriented direction, very similar to the southeast-oriented direction of the Delaware River here, and the southeast-oriented direction of Neshaminy Creek. And so I'm seeing some patterns here which suggest that the southeastern Pennsylvania drainage system is not explained by the hypothesis that this was the Delaware River was just a tributary to the Hudson, to a southwest-oriented Hudson River, that there's something more going on here than what that hypothesis explains. Now, if we follow the Delaware River south from Philadelphia, and here the Delaware River in Philadelphia makes a jog in a south direction and then continues in a southwest direction to Wilmington, Delaware, where it enters Delaware Bay. And Delaware Bay, as you can see, turns in a southeast direction. And Delaware Bay is a flooded estuary. It's a valley that was eroded by the river at a time when sea level was much lower, probably at a time when there was a continental ice sheet on the North American continent. And then as sea level rose, the valley was flooded. Now, why the Delaware River makes this bend here and didn't just continue in a southwest direction to Chesapeake Bay that you see over here is not real well explained, because there's really no reason why it couldn't have. In fact, there's a canal that's been dug between Delaware Bay and Chesapeake Bay, enabling boats to go through here. Well, that gives us one river. And I want to say that the Delaware River is not unique. I could have picked any one of several hundred rivers throughout the United States to show direction changes that are not well explained, barbed tributaries and water gaps that are not well explained. And my book is just showing a few of the examples and that are really just the tip of the iceberg of the unexplained evidence that's throughout the United States. And all of this evidence is anomalous evidence, which the accepted geology and glacial history paradigm cannot explain, and which geologists, for that reason, have been ignoring when they've been interpreting other evidence and building their paradigm on what must somewhere be some flawed interpretations that were made in the past. And I suspect that they were the interpretations of the northeast-oriented slope that I showed you and the northeast-oriented, the preglacial drainage system. The topographic maps make it very easy to see the anomalous drainage system and erosional landform evidence. And the map evidence can be used to develop a paradigm that is able to explain the evidence. In some future lectures, I hope to explain how the topographic map mystery developed, and I hope to explain how my efforts to develop a new paradigm able to explain the topographic map, drainage system, and erosional lands form evidence were successful, and what that new paradigm may mean. So with that, I'm going to thank you for listening and wish you a good day. That's the end of the